Hi everyone. Today I will be giving a pretty brief overview of study design and measures of effect in epidemiology. So let's briefly go through these learning objectives first. I want to start by talking about why we do observational studies in public health to begin with. And I will also tell you what the difference is between an observational study and an experimental one. And then we'll focus on three common types of observational studies: cross-sectional, cohort, and case control studies. And I'll talk about what the measures of excess risk are in each of those that we use. Specifically, I'll be focusing on relative risks and odds ratios. So let's talk about where we've been. Just as a reminder, at the beginning of the semester, we started talking about descriptive epidemiology, so those person, place, and time characteristics to give us an understanding of who's experiencing a health event or concern, where are they geographically, and what do trends look like over time. So those are all useful starting points for us to understand in the burden of disease or the health of a population. And we can use descriptive epidemiology to calculate things like incidence and prevalence. And often we use rates to express those so that different population sizes don't kind of interfere with our ability to understand the nature of the burden of disease for a population. And so descriptive data, again, are a great starting point. They're where we often do begin our work in public health, but they don't necessarily provide information about causal relationships. And by causal relationships, I mean, is a particular exposure, is a particular experience causing someone to develop disease or to have a bad health outcome? So that link, a direct link from an exposure to an outcome, is what we would call a causal pathway, a causal relationship. And that's ultimately what we really want to know, because if we want to change health outcomes, if we want to change the burden of disease in a population or improve a population's health, we need to know what those causal factors are so we can develop policies or programs to change them, improve them, address them in some way. So that's where analytic epidemiology comes in, moving from just the descriptive characterizing health and disease in populations to understanding why they are the way they are. And so just like in other kinds of sciences, we develop hypotheses, and typically we test those hypotheses using the analytic epidemiologic methods that we'll be talking about today. And often that involves designing some kind of study to look at whether risk factors are causing some kind of outcome, whether a particular exposure causes an outcome to happen. And the way that we most commonly express this difference is by calculating a measure of excess risk. Those could be relative measures, which is quite frankly what we usually report. So for one group compared to another group, what is the excess risk of having a negative health outcome? But there are actually absolute measures of risk as well. I won't be talking about them today, but attributable risk is kind of a companion measure to the relative risk. And attributable risk tells us that for a factor that is actually causing disease, what proportion, what amount of the overall burden of disease is due to a particular exposure. So, for example, at this point, we've pretty well established that smoking cigarettes, other kinds of things, causes lung cancer. And so we could actually say, if we could remove smoking from a population, by how much could we actually reduce lung cancer? Because as is usually the case, any particular disease or health outcome has more than one cause, and lung cancer is one of those cases. While smoking cigarettes is one pathway to develop lung cancer, you can develop it independently from other exposures, from genetic risk factors, etc. So we wouldn't eliminate lung cancer if we eliminated smoking, but we could reduce it by a certain amount. And so the attributable risk is an absolute measure of risk that can tell you by how much you could reduce the absolute value, the measured value of disease in the population. But most of the time, we're comparing different experiences, so an exposed group versus a not exposed group, and so we use a relative measure to express the risk, comparing one group to another. So what is an observational study? These are pretty common in epidemiology, and we spend a lot of time, if you go on to become an epidemiologist, go through additional training, you'll spend a lot of time thinking about how can we observe people and make meaningful comparisons? Because an observational study means you're just watching what normally happens. People make their own choices, or they engage in behaviors without influence from you, at least. Of course, there are multiple influences on behavior from people's environments. It's not really just an individual level choice, but we as researchers are not influencing that behavior directly. So we're not assigning them to a particular exposure group. We're not telling them to take a particular drug. We're not telling them to exercise more. We're just watching what happens when people go about their lives, engage in particular behaviors, and then we look at what their health outcomes are. So we're not randomizing anything. We're not doing any kind of intervention. And there are a number of reasons that observational studies are common. First of all, it's what's happening in life. So data are always potentially available that we could collect about a variety of health experiences. But the other reason we do observational studies is there's a whole multitude of exposure disease relationships that we're interested in that are completely unethical to randomize people to. So using smoking again, because it's a pretty obvious one, we know there are lots of negative health impacts of smoking. And so we're at a point where even if you think smoking might influence something completely indirectly related to lung function, if we want to look at the influence of smoking on cognitive health and Alzheimer's disease risk, we're not going to conduct an experimental study. We are not going to randomize people to smoke to see what happens to their brains later on, because we know that smoking is, in the meantime, going to negatively impact their lungs and potentially other parts of their bodies. So the only opportunity we really have available to us is to do observational studies where we just compare smokers, people who have smoked and people who haven't, and look at what their cognitive health looks like as they age. So that's why we're going to talk about observational studies. Experimental studies are the other option. So that is where we as researchers are intervening. We are determining what people are exposed to and not exposed to, and then following them forward to see who develops disease and who doesn't, and make a comparison. Typically, experimental evidence is considered the strongest level of evidence. And certainly in a well-designed randomized trial, that is the case. We can be fairly certain that it's not other things that travel along with the exposure that are actually causing the outcome to happen. In other words, experimental studies can really limit the amount of confounding and the amount of bias that occurs because of confounding in a research study. But it's also possible to do a not great experimental study. You still need to make sure that your sample is representative of the underlying population. You still need to make sure that people are randomly allocated in a truly random fashion, and that there's not some sort of inherent bias into who's getting exposed and who is not. So there's still things to think about and be concerned about in experimental studies, which I mention only to say that as you're reading the literature, if just because you see a randomized trial done does not necessarily mean it gives a more accurate result than a well-done observational study. My feeling is that a well-designed observational study can and often does give us the same result as an experimental study, and it has the additional potential benefit that we can look at a little bit more nuance of conditions and life history factors that go into various exposures. So that's the big picture. Observational studies is what we're going to be focusing on. So again, that group of studies where we are not, as the researcher, changing anything about what people are doing. We're just observing, we're watching what happens to different groups of people. So some people like to further subdivide observational studies into descriptive and analytic studies. I don't get too hung up on this, so I'm not going to spend a lot of time on this. But basically, cross-sectional studies, which are the first kind we'll talk about, often get classified as descriptive because we're collecting information at one point in time. So the argument is that you can't establish necessarily that one came before another. The other type that I will mention, because we're not going to talk about it anymore later in this particular discussion, is ecological studies. And ecological studies are different from the other types of observational studies because the unit of analysis differs. So for everything we will be talking about today, we're still talking about taking an individual person and asking them questions. all the measures, all the timing relates to an individual. In an ecological study, we're actually looking at groups as the unit of analysis. So we might be looking at schools or counties or even entire countries. And so we might be comparing, ecological studies commonly are used to look at policy differences. So if one state or one country implements a policy, how do health outcomes differ for that state or country compared to another state or country who didn't implement that policy? And clearly there are a lot of other things that travel along, especially at the group level, that might confound that. But the other major concern in ecological studies is that sometimes observations that are true at the group level do not hold at the individual level. So again, you could take a whole additional course on ecological study designs, but I just want to mention that they are typically seen as more descriptive kinds of studies, and they do potentially suffer from this ecological bias in which something that happens at the group level does not hold at the individual level. But we are going to talk about entirely individual level studies today, so we won't be too concerned about the potential for that type of bias. And then usually cohort studies and case control studies are considered analytic studies, those in which we are looking at people over time, and so we can establish the exposure actually causes the disease. So we'll talk about that more as we go along. Even if you do think cross-sectional studies are only really useful from a descriptive perspective, we still do them because they are, again, a good starting point, just like descriptive epidemiology more broadly is. They can help us generate hypotheses, especially in new areas where we don't have a lot of data. And oftentimes we can make use of existing data. So all the surveillance systems that we talked about earlier in the semester, the wide variety of data sources, including things like the census and medical records, already exist. And so it can be a little bit more straightforward, less costly, less time intensive to use existing data, but often it means that we will have a cross-sectional sample and won't be able to follow people over time. Okay, so I'm going to show some images that illustrate what these different study designs look like. So just so you have a sense of what these little stick people represent. The green ones are people who do not have the disease or the outcome that we're interested in, and then red figures generally represent people who do have the disease that we're interested in. So here, for a cross-sectional study, which again is commonly considered a descriptive type of observational study, we are sampling people from the source population without respect to their disease status. So we really do just take a subset, a cross-section of people. Again, hopefully this could be a random sample. That would be the ideal situation. But we take a group of people. Some of them will end up being people who have the health outcome we're interested in. Some of them won't. But we're not sampling with regard to their health status in any way. We're just trying to draw a random sample from the population. And then we ask them whatever questions are on our survey or are part of our study. And we're just asking about them at one point in time. So it's a simultaneous exposure and outcome assessment. So if you think about cross-section in biologic terms, if you're taking a cross-sectional slice of a cell or a sample of the earth, you end up with just one image, essentially one thin layer that represents the broader entity. And so it may accurately reflect what the rest of that cell looks like or the rest of that portion of the earth looks like, but it may not. And so that's kind of the limitation of cross-sectional studies. You're only getting one snapshot, one point in time, and you're using that to make some inference potentially about what's going on at the population level. So this may make you think of the measure prevalence that we talked about earlier in the semester, and indeed cross-sectional studies typically are our source of information about how many people are living with X right now. So how many people are classified as obese, or how many people have diabetes currently, or how many people have high blood pressure. So a cross-sectional study can answer those types of questions. I also think that cross-sectional studies, although they are only asking about a single point in time, They can also be useful because we can still ask people about their past history. So typically, we don't want to go too far back in time because people's memory for specifics of events tends to get worse when we ask about longer periods. But we could certainly ask people about the past week and the past month. What has your sleep been like? What has your mental health been like? And so we can use that kind of recent past information and look at current health outcomes. So I think there is the potential there for some questions to still use a cross-sectional design in a more analytic fashion so that we can establish, did some exposure come before a particular outcome? Let's see. So these are particularly useful for looking at patterns in the population. And again, we can look at relationships between exposure and outcome, but most of the time we probably aren't going to be very confident that they're causal since we're assessing them simultaneously. A cohort study kind of looks like a similar image at the start for our cross-sectional study, but here we are excluding people who have prevalent disease. So in a cohort study, you sample from your population. Again, you still want it to be a random sample if possible from your source population, but you start with people who do not have the health outcome that you're interested in, because a cohort study is a design in which we are going to follow people over time. So we start with people free of the outcome, and then we look at who develops the disease, who develops the health outcome over time. And so this is a measure of incidence. Cross-sectional studies gave us prevalence. Cohort studies can give us incidence. So within a population, how much disease develops in a defined period of time. And cohort studies tend to take longer. As a result, typically, we're following people for a long enough period of time that we get enough incident cases of the outcome. So for example, if you were looking at a chronic disease, many of those take years or even multiple decades for people to develop disease. So the cohort study might go on for that long. And things like the Framingham study have been going on for multiple generations at this point. Other cohort studies have been going on for a shorter period of time, but nonetheless, typically when you establish a cohort, the intention is that it's going to be a multiple year, multi-time point study. Now there are two ways to do a cohort study, and the kind I've been talking about has kind of been the prospective kind. So you actually sample people today who don't have the health outcome of interest. You separate your sample into an exposed group and an unexposed group who you're going to end up comparing the incidence of the outcome in these two subsets of your initial sample, and you actually follow them in real time forward, doing assessments and asking questions over a fixed period of time into the future. It is also possible to do a retrospective cohort study. So this would require that you have some kind of records available, typically medical records or maybe employment records, something along those lines, where you could essentially reconstruct a cohort study by going back in time. So the design is the same. You would still look, let's say 20 years in the past, identify a random sample of people from your source population, exclude anyone who already had the disease you're interested in at that point, and then kind of separate them into an exposed group and an unexposed group and follow them up to the present to see what the incidence of disease in those two groups was like. So that has the benefit of not needing to wait the 20 years that you would require if you were starting a cohort study now. But of course, the downside of a retrospective cohort study, or the potential limitation of one, is that you'd need to have existing records that give you the information that you need. So you'd have to have really good information about the exposure status so you could make sure you had correctly identified people at the start as whether or not they were exposed. Hopefully some interim measures in the meantime to look at how their exposure might have changed over time, in addition to having good information about when specifically they developed disease. And you'd want to make sure you had information on covariates, potential confounding variables along the way. So not always a possibility, but lots of Lots of great retrospective cohort studies have been done as well. And so it still gives us the robust design and information you would get from a prospective cohort study. It just doesn't require the time for follow-up. So again, the steps to do a cohort study are you always need to start by defining what your population is and clearly identify what your primary exposure is going to be for the study. Get a representative sample of people who have both been exposed and not exposed, again, so that you have enough people in each group to be able to go forward to follow incidence over time, follow up with them, and then at the end compare the incidence in the two groups. So here's just another kind of graphical or figure-based way to represent that. If we wanted to know if hormone replacement therapy increased the risk of MI among postmenopausal women, we'd start with our sample of postmenopausal women. We'd need to make sure that none of them had the outcome of interest, so none of them had had a heart attack before. Then we'd classify them. Again, this is not an experimental design, so we're not giving them hormone replacement therapy. We would just be doing a study in which we classify women as using hormone replacement therapy or not, and then follow each of those groups forward into the future and look at the incidence of MI among each one. And as I've noted at the bottom, you know, the incidence of MI for hormone replacement therapy users is just this number of women who had an MI out of the total number of hormone replacement therapy users. And then we calculate the incidence rate for the unexposed group. So the number of MIs out of the total number of women who had not used hormone replacement therapy. And then our relative risk measure is just the comparison of those two incidence rates, the incidence rate for the exposed group divided by the incidence rate for the unexposed group. And that tells us how much more likely or how much less likely hormone replacement therapy users were to experience MI compared to non-users. So risk, as a reminder, just means probability. It's essentially the chance that something happens. And so usually we're talking about the probability that somebody develops a disease or a health outcome over a certain amount of time. And also remember that the population at risk is anyone with a non-zero chance of developing that disease. So in our hormone replacement therapy example, you know, we were talking about postmenopausal women. So they have to be postmenopausal to be included in this study. They have to be at risk for an MI, and essentially anyone who has a heart is at risk for an MI. So that's fine. We don't need to further restrict our sample. But there are lots of examples that might be sex specific, or that people needed to have some existing disease. You know, we might be doing a study of amputation risk among people with diabetes. So our population at risk is people who have diabetes and have at least one lower extremity that could potentially be amputated. So just keep in mind that you need to define your denominator, your sample, according to what outcome you're looking at, because they need to have some risk. It doesn't need to be high risk, but they have to have a non-zero chance of experiencing the outcome of, you know, becoming an incident case during follow-up. And again, the risk ratio is the measure, the relative measure that compares the risk in one group to the risk in another group. So typically in epidemiology, we're talking about the risk of the outcome in the exposed group compared to the risk of the outcome in the unexposed group. And so a relative risk is what we would want to calculate. A relative risk tells us that it's that incidence ratio. What's the incidence of the outcome in the exposed group compared to the unexposed group? But there are reasons, which I'll touch on briefly as we go along, that we can't always calculate the relative risk directly. So there is another type of risk ratio, the odds ratio, that we often calculate instead. But let's start by talking about the relative risk. For any type of risk ratio, either relative risk or odds ratio, the potential values range from 0 to infinity. And 1 means that there's the same risk in both groups. Because remember, we're dividing incidence measures in the case of relative risk. So if the incidence in the exposed group, if the incidence of MI among women who used hormone replacement therapy was, let's say, 5 per 1,000, And the incidence in the non-hormone replacement therapy group is also 5 per 1,000 women. When you divide those two, you get a 1. So a 1 means that there's identical risks in both groups. Now, if the risk of MI for the hormone replacement therapy group was 5 per 1,000 and it was only 1 per 1,000 in the non-hormone replacement therapy group, our ratio would be 5 divided by 1. So women who used HRT would be 5 times more likely to experience an MI than women who didn't use hormone replacement therapy. So greater than 1 means the risk in the exposed group is higher than the risk in the unexposed group. Conversely, if the risk in the exposed group is lower, we often consider that a protective factor. So let's say hormone replacement therapy actually reduced the risk of MI. So maybe their incidence rate is 1 per 1,000 women, and the unexposed group is actually 5 per 1,000 women. So we'd have a relative risk of 1 over 5 or 0.2. And that would mean that women who use HRT have 0.2 times the risk of experiencing MI as women who don't use it. So on the protective side, the value can only range from 0 to 0.99. So it's kind of a compressed scale, whereas on the flip side, on the greater than 1 side, it can go up to infinity. So it's really only important to recognize that, because when you're interpreting them, we'll talk, when we go on to thinking about causal inference in more detail, we'll talk about how strong associations are. And by that, we mean how far from 1 is the risk ratio. And so just keep in mind that a relative risk of 0.2 is actually equivalent on the reverse side to a relative risk of 5. So you can invert it and invert the interpretation if it makes it a little easier for you to think about it that way. Okay, so this again just tells you how you calculate the incidence, the relative risk. Again, it's just incidence rate in the exposed over incidence rate in the unexposed. And here's that interpretation in words. So the last type of study I'm going to talk about is a case control study. And in this one, this is always a retrospective type of study. So sometimes it can be difficult for students to tell the difference between a retrospective cohort and a case control. And so the difference is because they're both looking back in time. In a case control study, we take our source population, take a sample from it, but in this instance, we are sampling by outcome instead of exposure. So in cohort studies, we have an exposed group and an unexposed group who we are following through either real time or past time to see who developed disease. In a case control study, we're actually sampling people based on whether or not they have the disease. And then we ask them about their past exposures. So the rationale for this is essentially if you have a really rare outcome, so maybe some kind of cancer that's really uncommon or a genetic disease that's really rare, if you just took a essentially random sample of people from the population and followed them over time, you might never end up with any cases or enough cases to say anything meaningful about statistically. So a case control study is a way to get enough people with the outcome in your study so that you can actually make some inference about what might be causing it. So you start with a certain number of cases, a certain number of controls, and often, again, for statistical reasons for power, we often do 2 controls to every case or 3 controls for every case. So we often, by design, choose more people without the disease than people with the disease. And so partly for that reason, you cannot calculate incidence from a case control study because we as the researchers, you as the person designing the study, are determining what the incidence, so-called incidence, is by deciding whether it's a 1-to-1 ratio. That would make it look like the incidence was 50%. If you chose 1 control for every case, that would give you a false incidence rate of 50%. If I decided to do 2 controls for every case, then 1/3 of my sample would have the disease, and that would give me a false incidence rate of 33%. So it's important to note you cannot calculate incidence from a case control study because you're setting how many cases there are and how many controls there are. But we can instead calculate the other type of risk ratio measure, the odds ratio, to estimate what the relative risk would be. So we still set up the calculation in the same way. The odds, I'm also not going to go into a long discussion here. Odds is related to probability, so it's calculated as the probability over 1 minus the probability. So it's not directly the risk. We're not talking about probability directly, but it's a related measure. In the scale is the same as for a relative risk, and the interpretation is similar, but we need to substitute the word risk from a relative risk interpretation to the word odds, because again, we're comparing the odds of the outcome, not the risk of the outcome changing. But one still means the odds are identical in both groups, and odds ratio, as I say here, of 0.5 means that people who are exposed have half the odds of developing the outcome as people who aren't exposed. And we calculate this by doing cross multiplication, so cell A times cell D divided by cell B times cell C. And I do want to note that when you might remember from biostatistics that when we run a logistic regression model, an odds ratio is what we get out. So we use these a lot, even for cohort and cross-sectional studies, because we often use regression models to do our calculations. But it's very important to note that the odds ratio is only a good approximation of the relative risk when the outcome is rare. And by that we mean that the true prevalence in the population of the outcome is probably about 5% or less, because after that, the odds ratio and relative risks does diverge quite a bit. So again, we could have a much longer conversation about that, but I just want you to know that an odds ratio is not the same as a relative risk. It does not mean exactly the same thing, especially when we start talking about really common outcomes. So that's important to note, and we'll come back to that in another video when I talk about causal inference. So next we will talk about causal inference, because once you do one of these studies, is that proof that the exposure causes the outcome? Not necessarily on its own, probably not on its own. So there are a number of criteria listed here that we will talk about. You do want to think about how strong that association is. So in other words, how far from 1 is your risk ratio measure. You do want to make sure that the exposure came before the outcome. So that's what we call temporal sequence, that we know the direction of the effect. And dose response is something else that could be relevant to what we've talked about today. Can you measure your exposure in a way that's kind of graded so that you can determine, does more exposure cause more of the outcome? Because that might make us feel more strongly that yes, this exposure is causing the disease. Consistency and plausibility are things that do not have to do with your own study design. Consistency means, did your study find similar thing, a kind of consistent message with what other studies have found? And plausibility means, is there some plausible explanation? Is there some mechanism that you could give for why this exposure might cause the outcome? And that could be a biologic mechanism like a drug action pathway, but it could also be some sort of theoretical or sociological explanation for a social phenomenon, like why would racism cause higher rates of cardiovascular disease? So it just means, is there an explanation, a scientific, well-founded explanation that you could give for why this exposure is causing the outcome? So as I said, we'll actually be talking about that more in another video. So hopefully that was a relatively clear, albeit brief, explanation of the different types of studies that we commonly use in epidemiology.